Hey, welcome back. You finished the beginner course. You know the theory. Now we go deeper. Episode 1, prompt engineering, RCTF, chain of thought, system prompts. Let's go. Hey, welcome back. If you finished the beginner course, you already know what AI is, what LMs are, and how agents work. Now it's time to go from knowing to building. And the very first skill every builder needs before writing a single line of code is this: knowing how to talk to AI properly. Because most people are doing it wrong. They type something like, write me a marketing email and get back something generic and useless. Then they assume AI isn't that smart. It's not the AI. It's the prompt. Let me show you the difference. The anatomy of a perfect prompt. Every great prompt has 4 parts. I call it the RCTF framework. R, role, tell AI who it is. C, context, give it the background it needs. T, task, tell it exactly what to do. F, format, tell it how you want the output. Let's compare. Bad prompt, write me a marketing email. Good prompt. You are a senior copywriter for a SaaS startup. I'm launching a new AI tool for small business owners. Write a 150-word cold email with a subject line that drives opens, a 1-sentence hook, 3 bullet point benefits, and a clear call to action. Keep the tone friendly but professional. Same request, wildly different outputs. The good prompt doesn't leave anything to chance. It tells AI who it is, what the situation is, what to produce, and how to format it. That's RCTF. Use it every time. Chain of thought prompting. Sometimes the problem isn't the output format. It's that AI rushes to an answer without thinking. Chain of thought prompting fixes that. You add one simple phrase, think step by step, or you can be more explicit. Before answering, waste out your reasoning, and then give me the final answer. This forces the model to reason through the problem instead of pattern matching to a fast but wrong answer. This is especially powerful for math, logic problems, debugging, and any multi-step task. Try it, so you'll see the difference immediately. Few shot prompting. This one is underused and incredibly powerful. Instead of telling AI what to do, you show it. You give it 2 or 3 examples of input and output. Then let it match the pattern. For example, say you want AI to categorize customer feedback. Don't just say categorize this feedback. Instead say, here are some examples. Feedback. The app crashes every time I open it. Category. Bug report. Feedback. Love the new dashboard layout. Category. Positive feedback. Can you add dark mode? Category. Feature request. Now categorize this. The search function never finds what I'm looking for. AI now has a template to follow. The output is consistent, structured, and exactly what you want. Use few shot prompting anytime you need. Consistent formatting or classification. System prompts. This is the secret weapon. A system prompt is a set of instructions you give AI before the conversation even starts. It shapes how the model behaves for the entire session. It's like giving someone a job description before they start work. For example, you are a no-nonsense senior engineer. You respond in bullet points. Like you never say, great question. You always explain trade-offs. You prefer Python. Now, every message you send gets filtered through that persona. You don't have to repeat yourself. The behavior is locked in. When you're building AI products, system prompts are where you define the entire personality, tone, and rules of your AI. This is one of the most powerful tools you'll use. Bad prompt versus good prompt. side by side. Let's do a quick before and after on 3 real scenarios. Scenario 1, debugging, bad. Why is my code broken? Good. You are a senior Python engineer. Here's my function. It's supposed to pass a JSON file and return a list of names. It throws a key error on line 12. Explain what's wrong and fix it. Show me the corrected code. Scenario 2, writing, bad. Write me a LinkedIn post. Good. You are a LinkedIn content strategist. Write a post for a software engineer, sharing a lesson they learned about using AI in production. Use a hook that stops the scroll, tell a 3-sentence story, share the lesson, and end with a question to drive comments. Max 200 words. Scenario 3, learning, bad. Explain RAG. Good. Explain retrieval augmented generation like I'm a developer who knows Python. And basic APIs but has never worked with vector databases. Use an analogy. Then show me the architecture in 5 numbered steps. See the pattern? Specificity wins every time. Your challenge for this episode: take any prompt you've used recently, run it through the RCTF framework, add a system prompt if you're using an API, try chain of thought on anything that involves reasoning. You will get better outputs immediately. In the next episode, we go beyond the chat box entirely. We call the API directly. That's where the real power starts. See you there. Take any prompt you've used this week, run it through RCTF, add chain of thought, lock in a system prompt. You will get better results immediately. Next episode, we call the API directly. See you there. Welcome to episode 2 of the AI Intermediate course. Today we go from using AI in a browser to calling it directly from code. This is where you become a builder. Hey, welcome to episode 2. If you're still using ChatGPT in a browser tab to do serious work, this episode is going to change how you think about AI forever. Because here's the thing, the chat interface is just a window into a much more powerful system underneath. And builders don't use the window. They go straight to the source. That source is called the API. What is an API? API stands for Application Programming Interface. I know that sounds technical, but here's all it means. It's a way for your code to talk to someone else. Is the what I say software? Think of it like a restaurant. You sit at a table, you want food, you don't walk into the kitchen yourself, you talk to a waiter. The waiter takes your order to the kitchen makes the food, and the waiter brings it back. The waiter is the API. You make a request, the API delivers it to the AI model. The model generates a response, the API sends it back to you. That's it. Now you can order from any kitchen in the world. Your first OpenAI API call. Let's write actual code. First, open your terminal and install the OpenAI library with pip. Now look at the code on screen. It's only a few lines, but let me walk you through what each part actually does. First, we import the library and create a client. Think of the client as opening a direct line to OpenAI. Your API key goes here. That's how OpenAI knows it's you. Then we make the actual call. We tell it which model to use, GPT-4o in this case. Then we pass in messages, a system message that sets the AI's role, and a user message with what we actually want. And the response comes back, and we print the content. That's it. Run it. You just called GPT-4o from your own code. No browser, no chat box. Pure API keys, tokens, and how not to go broke. Your API key is your identity. It's how OpenAI knows it's you making the request and what to charge. Never share your API key. Never put it in code you upload to GitHub. Use environment variables. Now, about cost. Every API call uses tokens. Tokens are roughly 3/4 of a word. So 1,000 tokens is about 750 words. GPT-4o charges you per 1,000 input tokens and per 1,000 output tokens. The way to control costs, keep your system prompt short and precise. Don't send unnecessary context. And use GPT-4 for tasks that don't need the full model. A good rule of thumb. Test with Mini, switch to the full model only when you need quality, like structured outputs. Get JSON back, not paragraphs. When you're building a real product, you don't want a paragraph of text back. You want structured data you can actually use in your code. Look at the example on screen. The only change is in the system message. So we tell the AI it's a data extractor and that it must always respond in valid JSON. That's it. The AI reads the text, pulls out the name, email, and company, and returns it as a clean object. You can feed that directly into a database, a form, or the next step in your pipeline. You can also use OpenAI's response format parameter to enforce a strict JSON schema. This is what you want when you're building automated workflows where one output feeds into the next step. Anthropic Claude API, same idea, different flavor. Anthropic's Claude is a completely different AI model. So, but the concept of calling it is identical. Look at the code. You install the library, create a client with your API key, and make a request. The structure is slightly different. Anthropic uses a messages object at the top level, but the idea is exactly the same. One key difference: notice there's no system message inside the messages array. Anthropic handles that separately, but the output, you get text back, you print it, done, and when to use which model. Here's the honest breakdown right now. GPT-4o is best for coding, structured output, tool use, and vision tasks. Claude Opus and Sonnet are best for long documents, nuanced writing, and following complex instructions. Gemini is best when you need Google search integration or a very long context window. And the mini models, GPT-4o Mini and Claude Haiku, are best when you need speed and low cost at scale. My personal rule, use Claude for writing and reasoning, GPT-4o for code and structured tasks. Benchmark both on your specific use case. Now, always real world challenge. Build a function that takes any URL, fetches the page text, and returns a 3-bullet summary using the OpenAI API. Use the request library to fetch the page, pass the text as context, apply the RCTF prompting framework from episode 1, and return structured JSON. That is a real useful tool, and you just built it. Next episode, we go deep on RAG, how to give AI your own data so it stops hallucinating and starts being actually useful for your real world problems. See you there. That's episode 2. You now know how to call AI directly through the API. No browser, no chat box, pure code. In episode 3, we go deep on RAG, how to give AI your own data so it stops hallucinating. See you there. AI is lying to you, not because it's bad, it just doesn't know your data. By the end of this episode, that problem is gone. Hey, welcome to episode 3. Quick question. Have you ever asked ChatGPT something specific, like your company's refund policy or a document you uploaded, and it gave you a completely wrong answer? Sounded confident. was totally made up. That is called hallucination. And it happens because the model doesn't have your data. It only knows what it was trained on. Why LLMs hallucinate? LLMs are trained on a massive snapshot of the internet up to a certain date. Your internal documents, your database, like last week's meeting notes. None of that exists inside the model. So when you ask about something it doesn't know, it doesn't say, I don't know. It fills the gap with a confident sounding guess. That is hallucination. The fix is actually simple in concept. Before you ask the model your question, find the real answer inside your own data and include it in the prompt. Now, the model answers from facts, not memory. That is RAG, retrieval augmented Kinjisin Sion. The RAG pipeline, I have seen this destroy real products. A customer support bot answering confidently how it actually works. There are 6 steps. The first 4 happen once when you set up the system. The last 2 happen every time a user asks a question. Step 1, ingest your documents, PDFs, text files, database records, load them in. Step 2, chunk them. You can't fit a 100-page document into one prompt. So you break it into smaller pieces, usually 300 to 500 words each. Step 3, embed those chunks. This is where text gets converted into numbers, vectors that represent meaning. Similar text gets similar vectors. Step 4, store everything in a vector database. Chroma, Pinecone, Vice. These are built specifically to search by meaning, not just keywords. Then when a user asks something, step 5, you embed that question too and find the chunks whose vectors are closest to it. Those are the most relevant pieces of your document. Step 6, you build a prompt with those chunks plus the question and send it to the model. It now answers from your actual data. No guessing. Chunking. The part most people get wrong, how you split your documents matters more than most tutorials admit. Too small, 50 words per chunk, and you lose context. A sentence out of context means nothing. Too big, 2,000 words, and you hit token limits. You're also pulling in so much noise that the model can't focus on what matters. The sweet spot is around 300 to 500 words per chunk, with a 50-word overlap between consecutive chunks. That overlap makes sure you never lose the meaning that the boundary between two synonym or two pieces. For structured documents like contracts or technical specs, chunk by section header. For raw text, chunk by character count with overlap. Vector databases, pick for your stage. A vector database stores your embeddings and lets you search by similarity. Chroma is local, open source, and runs on your laptop with a single pip install. Start here. It is everything you need while you're building and testing. Pinecone is cloud hosted and scales to millions of vectors without you managing any infrastructure. Switch to this when real users are hitting your system. Fize is Meta's library, blazing fast, no server needed. Best for local first apps or offline tools where latency is everything. Rule of thumb, build with Chroma, ship with Pinecone. Building a PDF chatbot, the real project. Look at the code on screen. 5 comments, 5 logical steps. Let me walk through what each one actually does. Line 2, you load the PDF. 1 line, LangChain handles all the parsing. Line 7, you split the document into chunks. You pass in your chunk size and overlap. That is it. Line 11, this is where, the magic happens. 1 call, embeds every chunk using OpenAI's embedding model and stores the whole thing in Chroma, the entire indexing pipeline in one line. Line 14, the user asks a question in plain English. Your system embeds that question, searches the database for the 3 closest chunks, and returns them. Those chunks go into your prompt. GPT answers from your actual document, not its training data. This is exactly how enterprise AI works. Customer support bots, legal document analyzers, that is the whole pipeline, 5 lines. Teams spend months building this. You just learned it in 10 minutes. Now let's make sure internal knowledge bases, all of them are RAG under the hood. Your challenge, take any PDF in a resume, a research paper, a product spec, build a simple RAG pipeline that lets you ask questions about it. Use LangChain, Chroma, and OpenAI embeddings. Follow the 5 steps, ask 3 questions, get answers from your actual document. And here is the real test. Ask something that is not in the document. A well-built RAG system should say it doesn't know. If it starts guessing, your retrieval is not working yet. Next episode, we build your first real AI agent with tools, memory, and the reasoning loop that makes agents actually useful. See you there. That is episode 3. Your challenge is waiting. Pick a PDF, run the pipeline, get a real answer from your own data. Episode 4 drops next, your first real agent. Episode 4. Today we build a real AI agent. Not just talk about it. You already know what agents are. Now you see exactly how they work under the hood. Hey, welcome to episode 4. By the end of this episode, you will have working AI agent, not a demo, not a toy, a real one. The React loop is how every agent thinks. React stands for reason and act. Every single agent, whether it's built with LangChain or Auto, GPT, or your own code, follows this same loop. First, the agent reasons, or it looks at the goal and asks, what do I need to do next? What information am I missing? Then it acts. It calls a tool. Maybe it searches the web. Maybe it runs some Python code. Maybe it queries your database. Then it observes. It looks at the result and asks, is this what I needed? Do I have enough to answer? Then it reasons again. If it has enough, it writes the final answer. If not, it goes back around the loop. That is the React loop. And here is the thing. This is exactly how you solve problems as a human. You gather information, take action, check the result, adjust. Agents just do it automatically. Now, an agent without tools is just a chatbot. Tools are what make agents powerful. The 3 tools every agent should start with: web search. Connect to Tavily or Serpa, and your agent can now Google anything in real time. No training cutoff, live data, current events, competitor research. All of it, a calculator. Never let a language model do math with tokens. LLMs are bad at arithmetic. Give the agent a tool that runs actual Python math. Reliable, always correct, and before we go further, quick checkpoint. React loop, 3 essential tools. That is the foundation. Every real agent in production uses exactly this. Now let's talk about memory. Code runner. This is the most powerful tool. Your agent writes Python, runs it, sees the output, fixes errors, and tries again. Give an agent a code runner and it can build almost anything. Short-term memory versus long-term memory. Short-term memory is the context window. Everything in the current conversation. The agent remembers it perfectly, nothing gets garbled. But the moment the session ends, it is gone. Long-term memory, a real database, Redis, Postgres, whatever you want. At the start of each new session, you retrieve the relevant memories and inject them into the system prompt. The agent picks up where it left off. Right now, focus on short term. We go deep on memory architecture in episode 6. Now let's look at the actual code. Here is a minimal agent in LangChain. 3 imports, 5 lines of setup, and you have a working research agent. You create the LLM, you give it tools, you pull a React prompt from the LangChain hub, you create the agent, and you run it. The verbose equals true line is important when you are learning. It prints the agent's reasoning out loud. You can watch it reason, act, observe, and loop in real time. Leave that on while you are building. Run this and give it a research question. You will see exactly what a real agent does. Your challenge for this episode: build a research agent with web search using Tavily. Give it any topic you care about. Make it return a structured JSON with a title, a summary, and key takeaways. That is a real research assistant. You can use it today, right now, for that is episode 4. You now know how to build a real agent. In episode 5, we build an MCP server from scratch. That is where it gets really interesting. See you there. Episode 5. You are going to build your first MCP server today. MCP is the standard that lets AI talk to any tool, any API, any database you own. By the end of this, Claude can use tools you write yourself. Let's build it. Hey, welcome to episode 5. Before MCP existed, every developer connecting Claude or GPT to an external tool had to write completely custom integration code. Different format every time, nothing shared, nothing reusable. MCP fixes that permanently. Think of it like USB. Before USB, every device had a different connector. USB gave us one standard. MCP is USB for AI tools. You write a server once. Any AI client that speaks MCP, Claude Desktop Cursor, any agent framework can connect to it without any extra work. That is the entire point. One server works everywhere. Now, how does it actually work under the hood? An MCP setup has 3 parts. The client is the AI, the thing that wants to use tools. Claude Desktop is a client. Cursor is a client. Your LangChain agent can be a client. The server is the code you write. It exposes tools. It could read your calendar, query your database, or call any API you like. The transport is how they communicate. Most servers use standard input and output. The client starts your server as a sub-process, and they talk through text on the command line. Simple, clean, and deliberately low tech, so it works everywhere. Now let's building a real MCP server takes about 20 lines of Python. First, install the SDK, just pip install MCP. Then define your tools in a list. Each tool has a name, a description, and a schema that tells the AI what inputs it accepts. Then write your handler. When the AI calls your tool by name, your Python function runs. It can call any API, read any file, query any database. So the architecture is client, server, transport, clean and simple. Now here is the part most tutorials skip. Writing the actual server code is much easier than you think. Watch this. Whatever you want, then it returns the result as plain text. That is it. The server runs as a sub-process. No web server to deploy. No ports to configure. Just a Python script. To connect it to Claude Desktop, open one config file on your Mac, add your server name, the command to run it, and the path to your script. Restart Claude Desktop. Done. Claude can now call your tool. Like, here is what that feels like in practice. You ask Claude in plain English, what is the weather in Austin? Claude sees your tool, decides to use it, calls your Python function, gets the response, and writes a natural answer. The whole loop happens invisibly. Now think bigger. What can you build with this? A calendar server, Claude can read your Google Calendar, find free slots, schedule meetings, and summarize your week in plain English. A database server, connect Claude to your Postgres or SQLite database, ask questions in plain English, and get real answers from your actual data. A file server, give Claude read access to a folder of documents, ask it to summarize, find, or draft content based on what is already there. None of these are hypothetical. Each one is a Python script you could write this afternoon. MCP is becoming the standard fast. Every major AI company is adopting it. If you know how to build MCP servers, you can connect AI to literally anything you work with. Your challenge for this episode: pick one tool you use every day and build an MCP server for it. Your notes, your task list, your local files. Make Claude talk to your real world. That is episode 5. You can now connect AI to anything. Next episode is one of the hardest problems in AI: memory. How do you make an agent that actually remembers you across sessions? See you in episode 6. Episode 6, agents that forget are useless. Today we fix that with real persistent memory. Hey, welcome to episode 6. Here's the most frustrating thing about AI agents. You build a great one, have a fantastic conversation, tell it everything about your project. Next day, you open it again, blank slate. It remembers nothing. That is not an assistant. That is a stranger with a good vocabulary. Today, we fix it permanently. There are 4 types of memory in AI systems. Each one solves a different problem. In-context memory is the conversation you are having right now. The model has perfect recall of everything in the current window, but the moment the session ends, it is gone. External memory lives in a real database outside the model. You save important facts, user preferences, and project context. When a new session starts, you pull them out and inject them in. The agent wakes up already knowing the user. Semantic memory uses a vector database. Instead of storing exact text, you store embeddings of key information. The agent can retrieve by meaning, what do I know about this user's working style or convene, and get back the most relevant stored facts. Episodic memory is a log of past events, not just facts, but sequences. Last week, the user debugged their auth module. I found a JWT issue. They were happy with the fix. Agents with episodic memory improve over time. When should you use each one? Use in context for anything the agent needs right now in this conversation. Use external memory for user preferences, project context, and long-term goals. Anything that should survive a restart. Use semantic memory when you have large knowledge bases and need to retrieve by meaning rather than exact match. Use episodic memory for complex assistance that should 4 memory types. Most projects need 1 or 2. Now let's write the actual code. It is simpler than you think. It get better the more you use them. For most projects, you start with external memory. Add semantic when your data grows large enough to need similarity search. Redis and Postgres, 2 databases, 2 different jobs. Redis is an in-memory key value store, sub-millisecond reads. Perfect for user preferences that need to load instantly at the start of every session. You store a user's name, their current project, their preferred tone. When a session starts, 1 call to Redis, and you have everything. Fast, simple, always on. Postgres handles the richer stuff, full conversation history, past topics, task completions, things you need to query, filter, and sort. Store each message as it happens and pull the last few topics whenever you need them. Now, here is the pattern that ties it all together: the memory injection pattern. At the start of every single session, before the first message, you run one function. It pulls fast preferences from Redis. It pulls recent topics from Postgres. It builds a system prompt that tells the agent exactly who it is talking to. The agent opens already knowing the user's name, their current project, their preferred communication style, and what they were working on last time. That is the difference between a generic chatbot and a personal AI assistant. Not a different model, not more compute, just memory injected at the right moment. Your challenge for this episode: build an agent with persistent memory using Redis or SQLite. Make it store the user's name, their current project, and the last 3 topics you discussed. Next session, it greets them by name and references their project without being asked. That single feature makes an agent feel. That is episode 6. Your agent now remembers. Next episode, episode 7, we ship it to real users. Your AI works on localhost. Today we change that. After this episode, anyone in the world can use it. We've built prompt engines called APIs, set up RAG, built agents, created MCP servers, and added memory. But all of it lives on your laptop. Nobody else can use it. That changes today. We are shipping. FastAPI is the Python framework for wrapping AI. 3 reasons it wins. First, async support. AI API calls take 5 to 30 seconds. FastAPI handles them without blocking other users. Second, it auto-generates interactive documentation at the /docs endpoint. 0 extra work. Third, pydantic validation rejects bad inputs before your AI even sees them. And here's a real AI endpoint in 20 lines. You create a FastAPI app and an async OpenAI client. The pydantic model defines the request shape, text, and how many bullets you want. The endpoint calls OpenAI asynchronously, requests JSON output, and returns the result. Run it with UVcorn and visit localhost 8000 docs. You get a full interactive testing interface for free. That is your AI wrapped in a real API. API key security is not optional. It is a hard rule. Never put your key directly in code. Push that to GitHub, even a private repo, and bots scrape it within minutes. You get a multi-$1,000 bill. Right, everybody? Coach, put keys in a .m file. Just add that file to .gitinyor and load it with python.env. On Railway, set environment variables through their dashboard. And your code never touches the actual key value. Streaming is the difference between an app that feels broken and one that feels magical. Without streaming, the user security locked. Now the feature that makes your AI feel instant, and the final steps to get a live URL, waits 15 seconds staring at a blank screen. With streaming, text appears word by word as the model generates it. Same total time. Completely different experience. The code adds streaming response and makes your function a generator that yields each text chunk as it arrives. For any user-facing AI feature, always stream. 4 steps to a live URL. Push your code to GitHub. Connect your repo on railway.app under new project. Add your environment variables in the Railway dashboard. Deploy. Done. Railway auto-detects Python, reads your requirements.txt, and gives you a live HTTPS URL in about 2 minutes. The free tier gives you $5 of compute per month, enough for a side project. Every git push to main auto-redeploys. 0 configuration. Before you share your URL with anyone, add rate limiting. One person running a script against your endpoint can drain your OpenAI credits in minutes. Slow API adds rate limiting to FastAPI in 4 lines. You create a limiter using the requester IP address, attach it to your app, then decorate each endpoint with the limit you want. 10 requests per minute per IP is a safe default. Also set a spending limit in your OpenAI dashboard. Do that now. Your challenge for this episode: take your RAG chatbot or research agent from earlier episodes, wrap it in a FastAPI endpoint with streaming support. Deploy to Railway. Share the live URL. You now have an AI product on the internet that real users can access. One more episode, the final boss, multi-agent systems. Your AI is live. Real users, real URL, real product. One episode left. I'll see you there. This is the final episode. We go from solo agents to full systems and complete the intermediate stack. Welcome to episode 8, the final one. You have built every layer of the intermediate stack. Today, we go further. Multi-agent systems, how to measure whether your AI actually works, and where to go after this course. Here is the problem with one agent doing everything. You're asking a single model to be the researcher, the writer, the reviewer, and the quality checker all at once. That works for simple tasks. For complex work, it falls apart. The solution is specialization. An orchestrator agent breaks the goal into pieces and delegates. A researcher agent searches and returns structured notes. A writer agent takes those notes and produces polished output. Each agent does one thing well. The system as a whole does more than any single agent could. Here is how a real researcher-writer pipeline works in code. You create 2 agents using different models. The researcher gets GPT Pro Mini, which is fast and cheap. The writer gets GPT 4o, which produces higher quality output. Both are just async functions that call the LLM with a clear system prompt. The orchestrator calls them in sequence, passing the researcher output directly into the writer input. The key in insight: use the right model for each job. Speed where it matters, quality where it matters. This keeps cost low while maximizing output. LangGraph is for when your workflow needs to branch or loop. Linear function chains cannot handle this. If the writing quality is too low, go back and research again. LangGraph models your workflow as a graph. Nodes are Python functions. Edges connect them. Conditional edges route based on state. The state type flows through every node. All agents share one object. You define the graph, add nodes, add conditional routing, compile it, and invoke. LangGraph handles all the orchestration. Yeah, you just write Python. Most people ship AI they have tested by hand 3 or 4 times. That is not testing, that is hoping. The professional multi-agent systems built. Now, the skill that separates engineers from guessers, actually measuring whether your AI works. Approach is evaluations. You create a test set of known question-answer pairs. You run your agent against every test case. You score the results using an LLM as a judge. GPT-4 scoring your GPT-4 mini outputs on a rubric of accuracy and completeness. This scales to hundreds of test cases automatically. Set a target score. Anything below that score means your prompt or model needs work. That is how you improve systematically instead of guessing. Look at what you have built across 8 episodes. Layer 1, prompt engineering with RCTF and chain of thought. Layer 2, direct API integration with structured output. Layer 3, RAG pipelines with embeddings and vector search. Layer 4, agent frameworks with the React loop and LangChain. Layer 5, MCP servers and custom tools. Layer 6, memory systems with Redis and Postgres. Layer 7, deployment with FastAPI and Railway. Layer 8, multi-agent systems with LangGraph and evaluation. That is the complete intermediate AI engineering stack. Most developers working in AI today are at layer 2 or 3. You now have all 8. 3 paths forward from here. Path 1 is fine-tuning. Take open source models like Llama or Mistral and train them on your own data. Better performance for your specific use case, lower inference cost, full control. Path 2 is open source models locally. Run Llama 3 or Phi on your own machine with Ollama, no API costs. Your data never leaves your machine. Path 3 is the most important one. Build something real. You have all the pieces. Pick a problem you care about. Use the stack. Ship it. Get users. Iterate. That is how products are built. That is the course. You built the complete intermediate AI engineering stack. Prompts, APIs, RAG agents, MCP, memory, deployment, and multi-agent systems with evaluation. The gap between knowing and doing is where most people live forever. You now have the knowledge. You finished the intermediate course, 8 episodes, 8 layers. Now the only move is to build something real.